Hello, I'm Joshing. I'm here to present the final projects of course pattern recognition, and my title is Analysis of Machine Learning Approaches for Spam Email Detection. So this is my outline. First, I'm talking about the problems, and so in this section, I'll talk about the spam types, and then I'll talk about the preprocessed datasets that I use for implemented the spam email detector. And then I'll talk about three algorithms that I use to implement the spam email detector. Naive Bayes classifier, K nearest neighbor, and support vector machine. And then I'll talk about the experiment setup, and then uh, making the performance evaluation among these three algorithms. And lastly, the conclusions. Uh, so first, we need to know what is spam email. So spam email, basically, we can say it is the email that we are unexpected to receive in our inbox. And spam email meaning the bad emails, and the ham means the not harm emails. So at least three kind of spam emails. First, the junk emails. These emails are like the advertisements emails that just wanting us to buy products from their department store, their stores. And second, the phishing or spoofing emails. And these kind of emails all sometimes contains the link that when user click that link, they'll go to the website, and the website seems pretty normal. So, but actually, when you click in the link, they can store your credential information like social security number or account password. And C, the Trojan host emails. These kind of emails may contain virus that when you click it, when you open it, your computer may crash. So in order to have the solutions, you need to pay for them. And then the preprocessed datasets. So the datasets I used for implementing this project is from UCI spam email datasets. These datasets has total number of instances like 4,601 emails in this dataset, and it has 58 attributes, and 39% of emails are in spam class, and the last attributes in each tuple is used to determine this email is spam or ham, and the other 48 attributes represent the percentage of the word occur frequency in the email. So let's take a look at the figure 1. So these are the general steps for dealing with machine learning problems. So first we collect the raw data, and then we pre-process the data. And here we already got the pre-processed data sets. And then we train the model and validate the model before we use our model to test the new data. And then we can use the trained model to classify emails. And then finally analyze the results. So next, the existing approach. Here I'm going to talk about the concept idea of each algorithm that I implemented for the spam email detector. So let's talk about the naive Bayes classifier first. So The central concept of naive Bayes classifier is based on the Bayes theorem to determine if an email is spam or ham. And below is the formula of naive Bayes classifier. So on the left-hand side of the formula is the conditional probability of S uh, given that W occurred. So in order to calculate these values, we have to calculate O values on the right-hand side. So the probability of S given that Wi occurred represent the posteriori probability of the word Wi appear in the email that is spent. And then the conditional probability of Wi given that S occur represent the probability of the word Wi appear in the email that is spent. And then probability of S represents the prior probability that the email is spent. Then the probability of H represents the prior probability that the email is ham. And last, the conditional probability of Wi given that H occur represents the probability of the word Wi appear in the email that is ham. So after calculating all these values, we can use the formula to compare the conditional probability of S given that W occurred with conditional probability of H given that W occurred. So we can classify the email based on this formula. And the second algorithm that I implemented is the KNN algorithms. So the steps are listed below. So first, there are new data in testing datasets that needs to be classified into A or class B, like the figure 2 below shown. First, the KNN needs to calculate all distance between this new testing data and all the other training data. And we can select the method to calculating the distance. Like, for example, we can select Euclidean distance, or we can use Manhattan distance to calculate. And second, based on the value we selected for K, and in this case, figure below, we have K equals 3, selecting the nearest 3 distances to compare. So after setting the distance, we like in figure 2b, we have a circle that shown in the figure, and K we set to 3, so we need to compare uh, the value inside this circle. So finally, in the third step, we classify this testing data into the one that has more instance. So for our example shown in figure 2b below, so we need to classify this new testing data to the class B, since that we have 2 green data inside this circle. So we are going to talk about the k-value selection. So small k value, that means that we are trying to fit every data in model, but these may lead to us that we are actually learning a lot ambient noise that may lead to overfitting. And on the other side, when we use large K value, we are just classifying the testing data based on the majority class. So these are some we need to be careful when we selecting the k-value. So the last algorithm is the support vector machine. So the concept of the support vector machines is to find the best hyperplane to separate different classes and maximizes the margin. So we can see in the figure 3 below. So we need to maximize the margin. That is the gray rectangular area. So based on the support vector are those three data. So this hyperplane based splits the data since it is as far as possible from these supports vector. So we can see from the right figure below that this figure means that we are classifying the new data, the yellow one, to which class. So for this case, we have a recipe that have ingredients, butter and sugar only. So we have a two-dimensional diagram here shown this scenario. So for this case, we are certainly need to classify this data into the muffin class, since we are on this side of the muffin. So support vector function have some parameters, so we are going to talk about them. So first, support vector machine function can do the regression and also the classification. So for our case, so for my project, I select using the SVC, stands for support vector classification. And support vector function is also able to classify high dimensional data. So from our last example in classifying muffin or cupcakes, we have just two attributes. So we have two-dimensional diagram shown in the last page. However, it can also classify data that with more than two, like if we have three attributes in our data, that means that we are in the three-dimensional space. So as shown in the figure 5. So it can also classify the data with more than three attributes, but it just that human beings cannot visualize the scenario when dimensional is above 3. So next parameters, C. The C parameters means that we are asking the support vector machine function to prioritize simplicity or to prioritize making fewer mistakes, like in figure 6 shown. So the left hand side of the figure 6 is we choose to prioritize the simplicity. So for figure 7, we are choosing to prioritize to making fewer mistakes. So this may lead to overfitting. And the fourth parameter, so we can specify the kernel to do some different things, like so let's take a look at the figure 9. So the distribution of these data set are in nonlinear separable data sets, so we cannot use a a straight line to separate two classes, but for support vector machine, we can specify kernel to using the RBA function, which means for radial basis functions. So then we can classify uh, nonlinear separable datasets like in figure 10 shown. So next, I'm going to talk about my experiment setup. So I set these four experiments setup in order to see the results of accuracy and evaluate the efficiency of each algorithm. So for naive Bayes classifier with Gaussian distribution, I vary the size of training data sets from 10% to 70% and then plotting the confusion metrics to check. And for multinomial naive Bayes, I also use vary the size of training data sets from 10% to 70% and then plotting the confusion metrics. And then for k nearest neighbors, I also vary the size of training data sets from 10% to 70% of original data sets. And also I will need to vary the k value 10 times to see which k should I select for each size of training data sets. And I I vary the k value from 1, 3, and then to 19 for uh, each each size of training data. And then I also plot in the confusion matrix for KN also. And last, for support vector machine, I first vary the size from 10% to 70% or so as training data sets, and then plot in the confusion matrix. Next, I'm going to talk about the performance evaluation for naive Bayes classifier. So, the figure and the table shown on the right hand side are the results of implementing the naive Bayes classifier. So, let's see when we use small training data sets that we will observe. So we can see from the figure that the multinomial naive Bayes is better than the naive Bayes. We can prove it by seeing the confusion matrix. So, like when I use 10% or 20% as training data sets, we can see that uh, the accuracy is far more higher than the naive Bayes for multinomial naive Bayes classifier. So, and also, we can see that the confusion matrix for 10% training data sets for a naive Bayes classifier, we have two zero values in the first column, which means, and also for 20% of training data sets, we also have two zero values in the second column. This means that this classifier is not doing any predictions. It's just guessing. So we cannot accept the result like this. But however, you can see from the multinomial naive Bayes, we have values inside four elements of the confusion matrix, both in 10% as training data set and 20% as training data sets. So second, we can observe that the appropriate training data set size for both naive Bayes and multinomial naive Bayes uh, are both in 50 to 60% as training data sets. Then the efficiency of the algorithms. So we can see from the figures 14 that there's not much difference between them. They are actually the same. And then the overall performance, it's obvious that multinomial naive Bayes did a better job than naive Bayes classifier, as we can see from the table 2. The accuracy is always better than, not always, is uh, relatively larger, better than the accuracy for the naive Bayes classifier. Next, the performance evaluation of k nearest neighbor. So first we want to see how to decide a k value. And from the figure and the table shown on the right, we can conclude that there's no simple rule to decide which k value should we select. So, and also the second thing that I just observed is that don't use the large k value that comes with higher, because like we can see from the figure 16, the the top line in green color, the as k value increases, we first decreases the accuracy, and then we jump high when the k value is around 11. However, we decreases the accuracies again when k value greater than 11. So we don't need to select a large k value with higher accuracy, because these may lead to overfitting. And then we're going to discuss the efficiency of the algorithm. So from the figure 17, we can conclude that the efficiency doesn't depend on the k value, since when k increases, the execution time steals on the horizontal line. And so the overall performance, so we can see that when we use uh, the training data set size equals to 70% of training data sets, we can get much better performance, since that we can see from figure 16 and figure 17 that uh, we have highest accuracies in figure 16, and also we have relatively smaller execution time as shown in figure 17. And then the performance evaluation of the support vector machine. So small data sets size, training data set size works no problem for confusion metrics. So as we can see in figure 18, that uh, we have we don't have those problems that occur in naive Bayes classifier that have zero values in one column. So we can conclude that uh, they works no problem with smaller data set, training data sets. Oh, and then the efficiency of the algorithm. So we can see from the figure 19 that the execution time is proportional to the accuracy. So before I jump into the conclusion, I want to show you uh, my program execution. So let's jump into the Jupyter Notebook. So here, so let's begin with knife-based classifier. So these are the code for implementing the knife-based classifier. So let's see. So I'll run it again. So as you can see, I start from using 10% as training data sets to 70%. So it works. Oh, sorry. Okay, let's see the results. So this program is that I use for plotting the result for uh, writing the final project reports. So here you can see that I start from this cell. Oh, sorry. Oh, because I didn't, I need to start from this cell. Yes, try it again. So, yes, it works. Okay, sorry again. So let's see the second algorithm that I implemented, the KNN algorithm. So, okay, the same. The source code are shown in here. However, for KNN, because it takes a lot of time to run, uh, because KNN is a relatively slower efficiency, and it also varies the k values from 1 to 10, no, from 1 to 19 10 times. So, and also for each experiment setup, so it takes about 1 hour to executing this program. So I'll just show when the first results comes out, or I'll just stop. So you can see that I use from 1 to 8, like that is for 10% to 70%. So let's wait. Still. However, let's jump into the third algorithm first and then see the result back. So the third algorithm is the support vector machine. So here again is the source code. So let's run it. Yes, it works. So okay, let's see the plot program for the support vector machine. It's here. So let's see. Yes, it works. Okay, let's see. However, it doesn't come out. Okay, let's talk about the conclusion. So, so the conclusion is that there's no simple rule to solve machine learning problems. So it all depends on the dataset size that we use and the expected accuracy and the efficiency that we want. So there's no simple rule to say that one particular method is always better than the others. So let's say example one. So a multinomial naive Bayes always better than naive Bayes classifier. So what if we shuffle the data sets? Uh, Maybe this time the naive Bayes classifier will be better than uh, the results from the uh, multinomial naive Bayes classifier. The shuffle data sets that I mean here is that uh, because I didn't shuffle the datasets to implement the the spam email detector. For example, like 20% of the spam email are in the later parts of this data, so that we can just use half half percentage of the spam emails for training. So the majority of uh, the the emails are in uh, ham class. So what I mean here, what I want to say is that if we balance the class in ham and in span, maybe we can get the better results. And the example two is that uh, do we need to always choose the algorithm with best accuracy? Uh, that is that when we use 50 to 60% as training, the KNN algorithm with k equals 5 have better performance than the multinomial naive Bayes. But however, we can see from the table that the efficiency of KNN is 25% worse than the multinomial naive Bayes, like here we can show in here. So you see that when we use 50% of training as the training datasets, the execution time for multinomial naive Bayes takes just 2.5 seconds. However, we need to take 50 seconds to execute the KNN algorithm. So it's obviously uh, the efficiency of multinomial naive Bayes is better than the KNN algorithm. Example 3, similarly, so we can track execution time for higher accuracy. So for both 50% as training data sets in support vector machine and the multinomial naive Bayes. So we can see like so we can train because support vector machine um, takes a little longer than the multinomial uh, Bayes, nominal Bayes, but the efficiency we can jump like 3%, around 3% higher than uh, using the multinomial naive Bayes classifier. So we can think about this when we doing uh, the implementing spam email classifier. So finally, uh, assume that we want to prioritize the accuracy only. Then under these conditions, we have naive Bayes classifier with 81.315% of accuracies. For multinomial naive Bayes classifier, we have 79.922% of accuracy, and for KNN algorithms, we have around 80%, 80.45% of accuracy, and the support vector machine with highest accuracy around 85.88%. So for doing this project, implementing the spam email detector, I would choose uh, using the support vector machine algorithm to implement it because uh, it gave it, it gives us the highest accuracy. So thank you. This is my presentation for my final project. Thank you.